Thank you, David. Good morning, everybody. My paper, Aerodynamic Drag in a Windy Environment. This paper is an attempt at a theoretical estimate of the unsteady drag component produced by an unsteady environment. And following on from Steve's interesting first paper, I've applied it to the wind average drag. Okay. I'll say a few words by way of introduction, mention again the WLTP. We'll discuss very briefly the natural environment that the vehicle exists in. Look at the effect of yaw on drag. At this stage, we're still repeating essentially what Steve has already covered. I'll also reintroduce wind average drag to you, but I'm relying heavily upon what Steve's already introduced. We'll look at the computation that I've used to derive an unsteady drag and the application of that to the wind average drag coefficient, and then draw some conclusions. Very briefly then, the WLTP is supposed to be a procedure that will improve on the published fuel economy data for passenger cars. I don't want to, again, look into the details of what's been proposed other than to repeat what Steve's just mentioned. It mandates in the wind tunnel testing that is part of that test procedure that moving belt ground simulation must be employed, but it also says it's got to be in very low airstream turbulence, and it's also only identifying the drag at zero yaw. And if we look very briefly at the actual environment that the car sits in, on the left-hand side, there the wind tunnel provides a very uniform flow conditions on the car. In reality, our natural wind input has turbulence. It includes shear and is also unsteady. The vehicles also tend to be acting in the presence of other vehicles. And this paper is an attempt to quantify the penalty that we get from not including these effects of the natural wind. Again, a few drag yaw characteristics for, in this case, some small hatchback cars, because at Tata that's the vehicles that we're primarily interested in. These drag curves tend to be slightly more parabolic than the interesting drag data that Steve was showing you earlier. But if we look at the range of values that we've got, again, I'm applying a simple parabolic rule to the drag relationship with yaw, because that's an easy one to compute. And for yaw angles up to, no, not what I intended to do, sorry. For a small range of yaw angles, then the parabolic rule for these cars tends to apply. And if we look at the value k in our simple parabolic equation, then that varies from around 1, actually it's not 1, it's around 0.5 to around 2 for the case that I'm dealing with here. And that's the range of values that I'm dealing with in this paper. Again, back to basics, but this slide is just to remind you again that in the wind tunnel we have a car that I've done it again. Finger trouble here, sorry. We have a car that experiences a resultant velocity at some yaw angle, and these two parameters are functions of both the vehicle velocity, the wind velocity, and the angle at which the wind velocity is relative to the direction the car is going to, and our wind direction can be anywhere. This, by the way, Steve, is the reference you're probably looking for Jeff Carr's introduction of the Myra wind average drag term. And again, our wind average drag is a function of this CD psi term, which is a function again of car velocity, wind velocity, and wind angle. And in order to generate the different wind velocities that we deal with, then we have we use a weighting function to define the probability of a particular wind velocity, and as Steve's already said, we assume that the wind direction can be from anywhere between plus or minus 180 degrees. Our wind input, for the purposes of my analysis, comes from the world of building aerodynamics and is the basic von Karman spectra. And we have a longitudinal component and a lateral component that we need to consider. And we also need to take into account the length scales of the turbulence. Now, this wind data is derived along the wind vector, and the first thing we need to do is to convert those to along the resultant velocity vector and normal to it. So that forms the input to the computation process that I've used here, and so we break out the wind input PSD function for the longitudinal and lateral components along the resultant velocity vector. We then apply a transfer function that relates the unsteady drag to the unsteady airspeed, and that gives us the individual drag components from those wind inputs. These we then sum together, and in order to take out the effects of the attenuation that occurs at high frequencies, apply an aerodynamic admittance function, and that provides the aerodynamic drag PSD. A typical PSD input looks a bit like this, where the red line is the drag from the longitudinal component, the green is the lateral component. These are summed together to give the blue spectrum, and then applying the admittance function gives us the purple line. You can see there it starts to attenuate above frequencies of 1 hertz. In this particular case, I've applied it to a particular car, done it again, and it's for a particular wind speed. So this computation has to be done for a full range of wind velocities, wind direction, and also for different car speeds. The RMS drag that we actually measure as a function of wind speed increases as the vehicle speed increases, and it becomes increasingly linear as we lose the effects of the parabolic function. If we then look at the RMS drag against wind angle, we can see at high wind velocities there is a why did it do this? It is essentially flat at very low wind velocities, but shows increasingly a peak at a certain wind angle at higher wind velocities. And then if we look at the way that drag varies for different wind angles, and I've looked at drag rather than coefficient, because clearly if we have a headwind or a tailwind, the drag coefficient is the same, but the drag is very different. And as we go from a headwind round to a crosswind to a tailwind, this is the variation of drag we get, and this effect is increased as the wind velocity is increased. If we look at then the effects on the drag coefficient, if we applying it for a particular k value of 1, and these are for different CD0 yaw values, then you can see the solid line is the wind average drag, and it changes from essentially 0 at very high car velocities and becomes increasingly significant as the car velocity reduces. If we look at the unsteady drag component, this has increased the drag quite considerably, and again the effect is increased at low velocities. Now, if we look at go back to our WLTP, the maximum speed in WLTP is around 36 meters a second. The average speed within the high-speed section is 26 meters a second approximately, but the average speed overall is only around 15 meters a second. So at these speeds, then both the wind average drag and wind average unsteady drag has become quite significant. Looking at the same thing for a given CD0 value of 0.3, as we change the value of K so that the car drag increases with yaw as K increases, then we can see again the solid values give us the wind average drag increasing very much as the car velocity reduces, but the unsteady drag component is considerably increased from that value. Just a few comments. I've applied the von Karman spectra in this case, but that's not really fully representative of what happens very close to the ground, where there's more energy at lower frequencies. I've assumed isotropic turbulence because that's the easy thing to do, and this will tend to overpredict the effects of the lateral turbulence component, but that's smaller than the longitudinal one. And increasingly, this parabolic relationship between drag and yaw isn't typical. of many recent cars, and where the drag rise with yaw can be very much steeper. And I conclude from that that the analysis may well underestimate the unsteady drag component. So to conclude, this is my attempt to understand the unsteady drag component. The standard measure of aerodynamic drag at zero yaw is really not representative of the real world, and we need to include the effects of steady and unsteady winds. The increase can be above zero yaw drag can be quite considerable, and these effects need to be considered when we look at real world fuel economy predictions. Thank you very much.